This is part 5 and hopefully the last part of a series that I'm making on geometrically interpreting the chain rule in multivariable calculus. My name is Bill Kinney. We're thinking about the chain rule, which is got this kind of formula here when z depends on x and y, and then x and y ultimately depend on u and v. That's the general formula. We're using it in terms of polar coordinates, and instead of u and v, we use r and theta, and the transformation capital Phi has this form here. We saw in the last video how to interpret this geometrically. We focused on this picture. We will again focus on this picture in this fifth video. But what I'd like to do to round out this series here is to actually deal with some numbers here. I'm going to type in some formulas here. In fact, the formulas you see right here, here, and here, to actually go ahead and figure out values of these derivatives, trouble typing, at specific points, so that the approximation ideas from the last videos will have a little bit more meat to them. I was just verbally describing some numbers in the last one, and so I'd like to actually figure out some specific numbers in this one. And actually that simplified, didn't it? I forgot to do that. Just negative 4 r squared cos theta sine theta. All right, so these are dz dr and dz d theta in terms of r and theta. And now I'd like to plug in specific points. Let's go ahead and plug in the point we were thinking about last time here initially, at about 1.25 for r and 0.75 or so for theta. In fact, let's pretend it's pi over 4 for theta. dz dr, let's think about what this is going to be geometrically, is supposed to be the gradient of f time dotted with a unit vector pointing in radially away from the origin based at the given point. Notice that the angle between the red and blue vectors here is very close to 90 degrees, and in fact, if I'm on that line at y equals x, it would be exactly 90 degrees. They would be perpendicular to each other, orthogonal, and therefore the dot product would be 0. Let's see if that happens when I plug in r equals 1.25 and theta equals pi over 4. I should get 0. Yep, I get 0. How about dz d theta at the same point? Let's try to make a guess about that. It's this dot product, this formula. As a dot product, it's the red vector dotted with the green vector. The angle between them looks like it's 180 degrees. The dot product will be negative, certainly. It would be the length of the red times the length of the green times -1, the cosine of 180 degrees, pi radians. So this length looks like it's about perhaps 2 or so, maybe a little bit bigger than 2. This length looks like it's about a little bit bigger than 1, perhaps. So I would expect something in the ballpark of -2 point something here for this quantity. Oh, I was off. This probably is longer than I was guessing, perhaps closer to 3 units long. This one is a little bit longer than 1. I can see it's longer than the blue. The blue one is 1 unit long. All right, let's try some other point. Just sort of pick an arbitrary point here, maybe right about there. It looks like r is about 1.5 and theta is about 1.1. 1.5 comma 1.1. Plug that into both of these derivatives. Let's make a guess as to the value. And also think about the, whether it makes sense in terms of the contour map. I should have done that with the last one. dz dr, letting r change a little bit, in effect moving along this blue line there a little bit. Certainly, you look at the contour map, it's going to be a negative derivative. The value of the function is going down. And in fact, the dot product between the red and the blue is going to be negative. The red's pretty long here, perhaps around 4 or so in length, and the blue is length 1, and the angle is perhaps 120 degrees or something. So length of the red, let's just say it's 4 times 1 times the cosine of 120 degrees or so, should be in the ballpark of -3 perhaps. And then with the derivative with respect to theta, we're increasing theta a little bit. If we increase theta a lot, the function value is going to go back up again, but if we increase theta just a little bit, the function value is going down. The instantaneous rate of change with respect to theta should be negative. And indeed, the angle between the red and the green here in this direction is perhaps about 140 degrees or something, and the green one's perhaps about 1.5 units long. So we should expect a -4 times 1.5, perhaps -6 or so. So I'm guessing for the first one again, it was guessing -3 something, and for the second one, guessing -6 or so. Although I was just guessing that the red one was about 4 units long. I don't know for sure. So -3. Okay, negative. What do we got here? The ZDR -1.76, so that's closer to 0 than I was guessing. Maybe the red one is not 4 units long. Maybe the angles between the red and the blue is not, or is bigger than I thought it was. And this one I was guessing it was going to be -6. I was pretty far off on that one, but it is negative. Let's pick one more point. Let me go up here. By the way, you can think about these rates of change in the graph on the left as well. You can see that if you're at this point in the graph on the left and you increase r a little bit, now it looks like the derivative is positive, and it looks like this derivative is also positive if you increase theta. And that's confirmed now by looking at this graph. Whether you move along the blue line or the green line, the function outputs are going higher because we're going toward a lighter region. And the red vector has an acute angle between both the blue and the green vectors. The cosine of the angle would be positive. The derivatives of both of these with respect to r and theta would be positive. Looks like r is about 1.4 and theta is about 2.5. I think I won't bother hazarding a guess as to the approximate values of these things, but again, the main thing I'm thinking about in trying to do such a thing is I'm thinking about these dot products, and I'm thinking about them, in fact, in terms of geometry. This dot product would be the same as the length of this vector times the length of this vector, which is 1, times the cosine of the angle between them. And the dot product here would be the length of that vector times the length of this vector times the cosine of the angle between them. They're both positive in this case, positive 0.8 and 3.8 or so. The derivative with respect to theta is bigger than the derivative with respect to r, which makes sense because r is practically parallel to that line there. So it's not, as you move radially away from the origin, it's not, the function value is not increasing very fast, but if you move along an angle, a constant r here a little bit, the function value is increasing relatively fast. So that's going to be the end of this series on the chain rule. Thank you for watching.